All right, today we are diving into something pretty wild. It's a look at a text that basically challenges the entire foundation of mathematics as we know it.
So, let me ask you this. What if the math you learned in school, the stuff that powers our phones, sends rockets to Mars, the very language of science, what if it's all built on a kind of mythology? I know, that sounds crazy, right? But it's a real claim, and we're going to unpack it.
And this quote from the author, John Gabriel, really gets to the heart of it. There are no axioms or postulates in sound mathematics. What he's saying is you can't just accept things as self-evident truths. No axioms. In his view, every single thing in math has to be built from the ground up, derived from pure logic.
Okay, Section 1, A Flawed Foundation. We're digging into the core arguments from a book called An Introduction to the Single Variable New Calculus. And yeah, its main idea is pretty shocking, that the foundations of the calculus we all learn are, well, just plain wrong. So according to the author, even the biggest names in the game, we're talking Newton, Leibniz, Cauchy, they all kind of missed the mark. The argument is that their work is just full of circular reasoning and concepts that, well, they just don't make logical sense. And this all leads up to the modern theory of limits, which the author sees as the final, flawed piece of the puzzle.
All right, so that brings us to the next big question. What exactly are these so-called ill-formed concepts? Let's take a look at the case against mainstream math.
And wow, here's the list of things the author basically throws in the trash. We're talking about infinity, infinitesimals, limits, irrational numbers, set theory, even zero as a number. The author calls all of this, and this is a direct quote, nonsense. It's not just a small tweak, it's a total rejection of the tools mathematicians use every day.
Let's just take irrational numbers for a second. You and I were taught that things like pi or the square root of 2 are numbers, right? Well, this author says, nope, they're not numbers. He calls them incommensurable magnitudes. Basically, they represent a real physical length, like the diagonal of a square, but you can't describe that length with a nice, neat fraction. And since his definition of a number is the name for a neat fraction or ratio, things like pi just don't make the cut. They're a different kind of thing entirely.
And you can hear it in the tone, right? The author is not mincing words. He calls the infinitesimal rubbish. But this is a huge deal. The idea of the infinitely small is what calculus is built on. So it really begs the question, if you get rid of all these fundamental ideas, what do you have left? How do you even start to build math from scratch?
Well, that's what's next. We're going to look at the author's new standard for truth. Before you can build anything, you need a blueprint, a test to see if a concept is even valid in the first place.
And that test is called the RACI requirements. It's an acronym, a four-step check for any idea. First, R for reifiable. Can you actually point to an instance of it? Can you produce one? Second, A for attributes. Is the concept defined by what it has, not by what it's missing? Third, C for contradiction-free. Pretty straightforward. Does it lead to any logical paradoxes? And finally, I for independent. Does the concept exist as a perfect, ideal form, completely separate from any human mind?
So let's apply this to something like infinity. It immediately fails that first test, right? The R for reducifiable. You can't produce an instance of infinity. You can't hold it in your hand. And from this point of view, if you can't do that, it's not a well-formed concept. It's just an invitation for the kind of paradoxes and fuzzy thinking that the author argues has infected mainstream math.
Okay, so if we can't use axioms, no, let's just assume this is true, where on earth do you start? The answer, according to this text, is you start with literally nothing, a void. And from there, you derive everything you need using pure geometry, just like the ancient Greeks.
I mean, just think about this for a second. Imagine a total void, absolute nothingness. If you ask the question, where? Boom, you've just created the concept of location or a point. Then you ask, okay, how do I get from here to there? That question gives you the idea of a path. And what's the most efficient path? The one with the fewest directions? A straight line. And from just those basic derived concepts, point, line, the claim is you can build all of geometry without ever needing to assume anything.
But what about numbers? Where do they come from? Well, in this system, a number isn't some abstract, floating idea. A number is just a name. It's the name we give to a measure that describes a relationship, a ratio between two things. So, you take two line segments, you compare their lengths, and that comparison, that's what a number is. It's born directly out of geometry.
And get this, the author claims that you can do all of arithmetic,
Addition, subtraction, multiplication, division, with 100% accuracy, just using geometric tools. No numbers needed. It's like geometry itself is a kind of ancient, perfect calculator. You can work with the magnitudes directly before you even need to invent names for them, aka numbers.
All right, so we've rebuilt the foundations with pure geometry. Now for the big one. How do you do calculus? This is where we get to the main event. The new calculus, a system built without any limits or infinitesimals.
So let's compare the derivative. On one side, you've got the mainstream calculus formula, with that whole limit as h approaches 0 thing, which can feel a little magical. On the other side, you have the new calculus formula. Look closely. There's no limit. There's no h approaching 0. It's just a clean geometric ratio. It's all about finding a secant line that runs perfectly parallel to the tangent line. It's a purely geometric construction. And the author makes a huge claim here that this is the first and only truly rigorous way to define a derivative. Why? Because it comes straight from geometry, and it completely avoids all the weirdness of the limit. There's no dividing by 0, no getting infinitely close but never touching. It's concrete. Okay, let's take a step back and just process all this. It's time to rethink mathematical reality a bit and pull out the key takeaways from this whole alternative perspective. So if we boil it all down, here's the core idea. 1. Mathematics isn't about axioms. It's derived directly from geometry. 2. At its heart, it's the science of measure and number. 3. Any concept you use has to pass that strict logical RACI test. And 4. Those things we call irrational numbers, like pi and the square root of 2, they're real. They exist as magnitudes, but they're not actually numbers.
And this quote really says it all, doesn't it? The clarity of ancient Greek thought has been unmatched. The whole argument is a call to go back to that source, to a time before all these, quote, ill-formed concepts supposedly led mathematics down the wrong path for the last 2,300 years.
And that really leaves us with a huge question to chew on. Now look, our goal here wasn't to tell you if this is right or wrong, but just to lay out this fascinating perspective. But if the very foundations of math, something we think of as pure objective truth, can be challenged this deeply, what does that mean for everything else we think we know for sure? What does that mean for the other truths we build our lives upon? Definitely something to think about.